Hi everyone, and thank you for tuning into our presentation. We are group number 7, and our group members include Jacob, AJ, Scott, myself, James, Sam, Musab, and Muath. Before introducing ourselves, here's a quick description of our project. When brainstorming ideas, our group was mainly focused on different types of games. We were looking to create something that would offer us some fun entertainment at the end and that we could be really creative with in the design process. Ultimately, we settled on designing a 3D printed pinball machine. Some general details of the machine include it being designed specifically for melt extrusion printing and for portability. My name is Haley Lang, and my main role in this project was presentation creation and meeting notes and follow-up emails to make sure everyone was on the same page.
Hello, I am Scott Bailiff, and my main role was the presentation creation and hosting meetings.
Hi, my name is Jacob Steer, and I helped create some of the CAD models for the playing field.
I'm James Sivich, and my main jobs were CAD designing and making some prototypes.
Hi, I'm AJ Puga, and my roles were CAD design and drawing standardization.
Musab is our 6th group member and is primarily focused on working on the CAD design for the upper right playfield zone. Our 7th group member is Muath, and his primary focus was working on the CAD design for the ball launcher and return systems. And our 8th group member is Sam, and his primary focus was working on the CAD design for the upper left playing field. On a large scale, conventionally manufacturing a pinball machine involves a variety of different processes and machinery, ultimately adding up to several manufacturers and hundreds of workers as well as thousands of parts. Plastic components are often molded, metal parts are made by a variety of molding or sheet metal forming processes, and the wood playfield is created by high pressurized treatment and usually a router or laser cutter. Scaling this down to a do-it-yourself pinball machine with conventional manufacturing is possible, but greatly limits how creative the designer can get and may mean parts will need to be bought. A 3D printed pinball machine allows simplicity in materials and allows the designer to make more complex parts, such as tunnels, loops, and other features that would be difficult to conventionally manufacture. So once we selected this as our project subject, we all created sketches of playfield designs and obstacles that we would like to be incorporated into the design. We also came up with ideas of how we would create sub-assemblies such as the flippers and ball launcher mechanisms. We also found inspiration online for what we each envisioned for this project and shared with the group.
The additive processes used within this project was primarily melt extrusion for additive manufacturing. We looked into different methods beyond this, but for this simplistic project, this was the most appropriate method to use. It offered one-off designs, faster production, and allowed more intricate parts than subtractive manufacturing or alternative methods that would be used in a conventional pinball machines. Things that made it not viable, though, would be if we had to mass produce this, produce a larger scale project, or even more intricate or involve more intricate electronics than we did in the flipper mechanism.
The pinball flippers were intended to be controlled by a pair of inexpensive linear actuators connected to the flipper as a sub-assembly seen here with a 632 machine screw. This is fastened to a metal nut embedded in our 3D printed part, the flipper crank. The metal nuts and the 1/4 inch hexagonal shaft passing through the playfield base are held in place in their hexagonal holes by an interference fit. This was accomplished by specifying a CAD dimension equal to the measured part. These holes then came out slightly undersized due to the melt extrusion process and resulted in the desired fit. The images seen here on the right show the prototype parts and the implementation of our embedded metal thread. The lower triangular bumpers consist of 632 bolts which pass through the playfield base and hold rubber bands and a top cover. The top cover was designed with a countersink that would be upside down in the desired print orientation. This countersink was specified at 30 degrees from the vertical direction to allow printing without any support structure or wasted material.
This slide shows the ball launcher and return designs. These parts were designed by Muath. For the ball launcher, a high elasticity spring is attached to the ball launcher in order to increase the resistance of the backward motion, thus resulting in a high force to kick the ball forward. And for the ball return, a simple slant allows the ball to slide all the way back to the ball return in order to start a new round of the game.
So the second floor obstacle is located on the left side of the playing field. And the big benefit to this design is that it's created in one part. In a conventional manufacturing setting, this could take multiple parts between 10 and 15 in order to create. As far as design aspects go for additive manufacturing, multiple angles were incorporated and drafts were incorporated to eliminate the significant need for support material. So some of the draft angles were incorporated into uh, the bolt holes so that no support material would be needed to be removed from those holes, and then as well as a 30-degree chamfer around the support legs to also make it easier to remove the support material supporting the second floor. This part is the right side obstacle, and it's located on the right side of the playing field. The part can also be printed in a single print, so no post-processing or assembly is needed. The channel is printed in a teardrop shape as to remove the need for support material that would be difficult to remove. The spinners, pictured in the bottom left, were designed as an articulating part where the ball can roll between them, causing them to spin. A 6-degree draft angle was made so the spinners would not be able to be pulled off of the single part. And a 30 thou gap was incorporated to accommodate for dimensional changes expected from melt extrusion.
The vertical loop is an obstacle that would be located in the upper left playing field. When it's printed in the direction shown in the image, it would not require any support material to print. This obstacle was designed with additive manufacturing in mind as opposed to subtractive manufacturing. With subtractive manufacturing, to make this part out of a solid piece, it would have a lot of waste material or would require a ton of these to be printed with sort of injection molding. And this part adds difficulty to the game where you can hit it and go in the loop or have the ball fly through the middle. The front and back legs were designed with additive manufacturing in mind. They have an articulating foot to account for uneven or bumpy play surfaces. The front and back legs are modeled to screw into the underside of the playfield and have their countersinks at a 30-degree angle, so it would not require any support material while printing. They have a height difference from each other to give a 6-degree incline for the playing field, which is the same incline that most standard pinball fields have. The playfield side, top, and channel are printed as the bounds for the playing field. These parts had additive in mind with their angles for the countersinks and the screw hole to not require any support material while printing.
This slide shows our bill of materials for all of our printed components. In the full bill of materials, we also include fasteners and the wooden base of the playfield. We plan to print most of these parts out of PLA with the option to print a few in ABS for higher durability. The flippers specifically would have been printed using the Onyx filament with the Mark Forge machine to give the parts more strength so they could withstand the continuous pinball impacts. In total, the weight for all printed parts comes out to 750 grams, meaning we would have been able to stick to one roll of filament. And we estimate the total cost of this project would have cost around $28, and the total print time was estimated to be 165 hours.
Looking at the dimensional tolerances for this project, the average pinball machine for a tabletop is about 30 parts, while a full-size pinball machine is up to 3,500 parts. On both of these machines, the playfield is required to be stable and smooth for the ball to roll along during the game. These machines operate on about a 5,000th dimensional tolerance for all plastic and aluminum parts with longer interfaces to maintain this smooth play surface. Because we utilized primarily melt extrusion for this project, we were working with a 10,000th tolerance and was able to work within that for this whole project. That's kind of proof here with the validation of the quality of our project. Before the shutdown, we were able to get one part printed on a home printer with PLA. And as you can see, compared to the nominal dimensions within the CAD drawing, all dimensions were within that 10,000th tolerance that we were aiming for. We were expecting this to be worse when we first started due to melt extrusion and this home printer, but we were purely amazed with the fact we were able to maintain this tolerance at the beginning. Looking at the cost analysis for this project, again, comparing this to real life pinball machines, tabletop machines range from about $40 to $50 to full-size machines average about $7,000. All of these machines operate on about a 15% profit margin. So for this tabletop machine that we're comparing to and that we built, they only take about $30, $35 to actually build. Our game took about $50 to build due to the $35 kilogram roll of filament, as well as $15 of outside parts we had sourced, such as the playfield surface and motors for the articulating flippers. These tabletop games would often use injection molding and vacuum forming for their construction, and that was able to drive the cost down for these mass-produced parts compared to our one-off project. Now, comparing this to full-size pinball machines, though, if we wanted to kind of implement additive manufacturing to reduce their cost, these machines take 2 weeks to a month to build, are 3,500 parts, use half a mile of wiring, and have a final production cost of an average about $5,000. If we could streamline a lot of these processes with additive manufacturing through mass production of injection molding, or even trying to implement singular parts across all machines rather than these many custom-built playfields, we could potentially reduce the labor cost, which is the largest price, by reducing the time it takes to manufacture these machines, as well as the straight-up material cost by up to 50%. Kind of looking at the lessons we learned throughout this project, looking on the design side, we found that for our group it was very easy to get lost in the details, and we didn't really account for any additive manufacturing processes at the beginning other than melt extrusion, just because that's what we knew best. When we actually took a look at the alternative methods, we found openings that would allow our project to actually be added upon. However, the ease of melt extrusion made us still stick with that as the primary method of additive manufacturing. We also needed to be more decisive early on. We hemmed and hawed a little bit on which project to produce from the beginning, but we decided if we just run with it, changes can always be made later, and that's something we had to keep in mind during the design. With that, we also had to never eliminate these ideas, no matter how weird they could be, because they might bloom into some other better idea down the road. Looking at the manufacturing side, which for this project became more of a CAD project due to the campus shutdown. But we found that coordinating a full project of this with many more intricate CAD files took a lot more cooperation and communication than we originally expected. We had to utilize a more scheduled team meetings format to actually make this happen. On top of that, when we were trying to look at creating a full assembly, the standardization of the fasteners made it so that the parts fit together easier in our full assembly. But with that, when we went to the full assembly, we found that there were always more problems that would generate. The other big lesson we had to learn from is when we were originally planning this project, we did not account for over 160 hours of print time. And when we're working with melt extrusion printers, there was a high chance of part failing if we weren't careful. So one major lesson we learned from this project was that with additive manufacturing, we always need to account for print fails and almost double the expected print time in case of these occur. With that, I would like to thank you all for listening to this, and we're going to wrap this up. So thank you again, and have a good day.
Nice.